Yeah, so my name is Henry Corrigan-Gibbs, and I'm going to talk about some work I've been doing at Stanford with Dan Bonnet and David Mazieres about a system called Riposte, which is an anonymous messaging system handling millions of users. So the setting that we normally talk about when we're talking about cryptographic protocols is one in which we have Alice and we have Bob, and Alice has some secret message that she wants to get to Bob over an insecure network. And the way that we usually do this is we have Bob generate a public and a private key for some public key encryption system. And then he gets his public key to Alice somehow. Alice then just encrypts her message with Bob's public key and sends it over the network. And the security property that we usually demand of such a scheme is that if there's an adversary listening in on the connection between Alice and Bob, the adversary doesn't learn anything useful about what Alice is saying. So with encryption, we can actually do a very good job of hiding the data, hiding Alice's payload. But I'm going to ask the question, does that really hide enough? Does that hide everything that Alice wants to keep secret? So in particular, if you look at what the adversary learns by listening in on Alice's network connection for a period of time, you see that the adversary can build up this sort of table. So he learns who Alice is talking to, the size of her packets, and the timings of those packets. And this doesn't necessarily look so bad until you swap out one of these fake names with the name of a real organization. So for example, taxfraud@stanford.edu is the email address we're supposed to contact if we suspect there's some tax fraud going on in our academic department. So in this case, just by virtue of seeing that Alice is communicating with taxfraud@stanford.edu, the adversary has learned something very interesting about Alice's message, even though he doesn't get to see her payload. So the point here is really that hiding the data is necessary to get the sort of privacy that you want, but in many cases it's not sufficient, because this metadata leaks a lot of information about what you're saying. So the goal of the system called Riposte that we've built is to allow a large group of users to get together, and I'll call this set of users the anonymity set. They run some protocol, and at the end of the protocol, everyone has posted a message to some public bulletin board. And the key security property is that no one knows who has said what. So there's sort of anonymity in terms of what you're posting to this bulletin board. So in practice, we'll implement the bulletin board with a set of servers, and we'll make some non-collusion assumptions about the servers. But I'll come back to that later. And basically the way it works is that every user in the anonymity set comes online over the course of a day and interacts with the servers somehow, so exchanges some messages with the servers. And so by the end of the day, every user has come online, and then the servers, once they've sort of gathered all these messages from all of the users, can add up their shares of what they've collected over the course of the day and recover everyone's plain text messages. So again, the key security property here is that the database servers don't learn who wrote which message. So the set of users is public. The set of messages that comes out at the end of the day is public, but we're hiding the association between users and messages. So that we keep secret who said what. This sort of protocol turns out to be really useful for building systems, all sorts of systems related to hiding the metadata. So you can think of anonymous Twitter as a direct application of this, anonymous survey platforms, private point-to-point messaging systems, systems that allow you to sort of leak information to a news organization and so on, all can use this as a building block or a primitive. And Riposte is not the only way to do this. There's other systems that come to mind when you think of this sort of messaging. So the first class are low latency anonymity systems like Tor, which are very good for browsing the internet anonymously. By design, though, they don't protect against an adversary that sees the whole network. So they're just not designed to protect against that sort of adversary. And if you are interested in protecting against an adversary that sees the whole network, you shouldn't use those systems. So mixed nets are another way you could think of achieving this. But typically, mixed systems require pretty expensive zero-knowledge proofs to protect against certain sorts of active attacks by the mixed servers. And as the number of users grows, the complexity and cost of these proofs grow too. And at large scales, they're not so practical. So Riposte is an anonymous messaging system that tries to sort of solve both of these problems at once. So we're trying to protect against an adversary that sees the whole network, that also controls some of the servers, and that controls many of the clients. So this is a very strong adversary. But we want to handle millions of users for this sort of anonymous Twitter application. So we really want to scale to network sizes that are close to internet scale, even though we're still defending against an adversary that's quite strong. So that's the rough motivation for this work. I'm now going to talk about a straw man construction, or first attempt construction, that should give you a little bit of intuition for how we build this. And then I'll go over a couple of the technical challenges that we had to solve to make this work before explaining how it works in practice. So the straw man scheme is relatively straightforward. We're going to have two servers, server X and server Y. And I'm going to make the assumption for now that they don't collude, and weaken this assumption later. But really, these two servers are holding shares of the state of the bulletin board. So the bulletin board starts out at the beginning of the day with all zeros. And you can think of this also as like a database. Like these two servers are holding shares of a database. And the users, as they're posting to the bulletin board, are really writing into the database without leaking to the servers where they're writing. So how does this work? Alice comes online, and she has some message that she wants to write into the database without leaking where she's writing. So she has some message to say she wants to write it into the third slot here. What she'll do is she'll stick her message into a big vector of all zeros. And this vector is going to be as large as the database is. So it's a big vector. And she generates a big vector of random blinding values, again, as large as the database is. And then she just takes the difference of these two vectors and sends one vector to each server. OK, now the servers, having received these vectors, just add them into their state. And then do the same thing with another user. So some other user, Bob, comes online. He does the same thing, sends his vectors up to the servers, and they update their state. So now at the end of the day, the two servers can come together, add up their shares of this database state. And what comes out is a vector of all zeros, except with Alice's message at row 3 and Bob's at row 5. So we sort of accomplished what we wanted to, at least up to a first approximation. So why is this not sufficient? Well, let me explain first what this does achieve, which is that you get information theoretic anonymity as long as the two servers don't collude. So as long as the two servers don't share their information with each other, their secret information, you get very strong anonymity properties. And you can actually weaken this assumption by adding more servers. So if you use k servers, you can get protection against k-1 servers that collude. The other neat thing about this construction is there's almost no heavy computation involved. This is just XORs over strings. And one other nice feature that we take advantage of is that unlike a mixed net, the storage cost here is constant in the size of the anonymity set. So the storage cost at the servers is really proportional to the size of the bulletin board or the size of the database, which actually can be much smaller than the anonymity set size if you're working in an application where there's many more readers than writers. So like Twitter or WikiLeaks or something like this. But we're not quite done. There's a bunch of reasons why the first scheme doesn't work. So here are a couple. I'm not going to talk about all of these. But so the first problem is if two users write into the same row of the database, they'll corrupt that row. So they won't get, neither message will get through. So we need to deal with that. We need to deal with malicious clients who send malformed vectors to the servers to try to corrupt the state of the database. And we need to worry about the bandwidth cost, so the cost between the servers and the clients. So for the first two things, I'm just going to point you to the paper. We have solutions for both of these problems. And if you're interested in how that works, you can check it out. I'm going to focus on the third one just to give you a taste of the sort of problem that we had to solve. So the challenge, sort of the core challenge is this issue of bandwidth efficiency. In the first attempt solution I described, each client needs to send a database-sized vector to each of the servers just to make a single write request. So if the database is millions or billions of rows long, that means to write a single message, you have to send gigabytes of data to each of the servers. And if you have millions of users, this is not going to work. So what we do is we use a cryptographic trick to compress the vectors. So instead of sending database-sized vectors, you send much shorter vectors. And this trick is based on private information retrieval protocols. So if you've seen them before, private information retrieval protocols allow you to read privately from a database. We're basically turning them on their head. So using a private information retrieval protocol to write into a database. And really, we can use some of the same tools and take advantage of the very nice literature on private information retrieval to work on this very different problem, which is anonymous communication. So the core sort of cryptographic primitive we use is called the distributed point function to achieve this. And these are also used in private information retrieval protocols. So if you haven't seen them before, this is how they work. There's a key generation routine that takes in a message and integer L, which is like an index into a vector. And it spits out a bunch of keys, so K1 up to Kn. And you can think of these as like short keys for a pseudo-random number generator. And the second algorithm associated with the DPF is very much like a pseudo-random number generator in that it takes a key and stretches it out into a very big vector. But there's a couple special properties of these algorithms, the first of which is that if you add up all of the resulting vectors, you get a vector of all zeros except with an m in location L. So these vectors have some very special structure. But even more than that, if you look at the keys, if an adversary, say, gets a hold of some subset of the keys, she can't learn anything about M or L. So the keys, in some way, hide the message M in the location L unless you see all of the keys. So how can we take advantage of this tool to reduce the bandwidth between the clients and the servers? The basic idea is to do this. So Alice now, instead of generating 2 big database-sized vectors to send to the servers, she just generates 2 DPF keys. Then she just sends 1 DPF key to each of the servers. The servers on their own can use this eval routine to stretch out these short keys into very large vectors, again, the size of the database. And then they add this vector into their state as before. And from there on, the whole protocol runs exactly as the earlier scheme I showed. And it turns out that you can actually construct DPFs that have very nice both security properties and efficiency properties. So prior work has shown that you can construct DPFs where the key size is like the square root of the length of the database. So if the database is gigabytes long, your DPF keys are going to be something like kilobytes. Even better than that, though, the 2-server version of this protocol just needs to use AES. So there's no public key crypto involved in generating or evaluating the DPF keys, which turns out to be a huge performance advantage. But then if you want protection against many of the servers colluding, so you want a DPF scheme with K keys such that if K minus 1 of them get leaked to the adversary, we can build those too. So we show a construction using public key primitives that is still efficient in terms of space, in terms of the key size. But of course, since it's using elliptic curve operations instead of XORs, it's going to be slower. So the last thing I'd like to do is just talk a little bit about the evaluation results, what this looks like when you try to implement it. So we actually implemented the whole thing in Go. We implemented the 2-server version and the multiple server version. And the bottom line result is that for a database with something like 65,000 tweet length rows, we can process 30 writes per second on a single server. So putting that in another way, we can process about 1 million writes in 8 hours on a single server. And this workload is completely parallelizable. And the reason for that is just because what the servers are doing is they're taking these DPF keys, stretching them out to the size of the database, and then adding them into their state. And you can do that operation in parallel on as many cores as you have at the same time. So if you want to triple these performance numbers, you just add 3 servers is an easy way to do that. And to give you some intuition on why we get the numbers that we do, this is just a chart of how the throughput in terms of the client requests that a single server can handle per second varies with the size of the database table. So on the left, when the database table size is very, very small, you're basically limited by how fast the servers can set up TLS connections with the clients. And then as the database table size gets huge, the servers are just spending all of their time doing AES to expand these DPF keys into long vectors. And at that point, basically the dominating cost there is just how fast the server can do AES operations. So to sort of come back to where we started, I mean, the world we live in today is one in which if there's an adversary listening in on your network connection, the adversary not only sees who you're talking to, but how much you're saying and when you're saying it. And with this sort of system, we'd like to move to a world in which if there's an adversary listening in on your network connection, the adversary just sees that you're talking to a Riposte server and you're saying fixed length things. And the adversary doesn't really learn much about what you're saying, right? Because it just learns that you're talking to Riposte. So I've tried to argue that hiding the metadata is, at least in many contexts, just as important as hiding the data itself, hiding the payload. And with this system called Riposte, we've shown that a combination of cryptographic tools and systems design principles can let you create these million user anonymity sets, which I should point out is something like 2 orders of magnitude larger than you can do with prior work that has the same security properties. And of course, the next step is to try to make this thing even faster, handle even larger messages with an even larger number of users. With that, I'd like to take your questions. Thanks.
Yep,
Right.
we have about 5 minutes for questions, so.
Okay. So this is indeed fascinating stuff. I have a specific question about the fact that, so you mentioned you are writing in the database. How about ORAM instead of PIR for that?
Could you say that one more time?
ORAM.
ORAM.
Yeah.
So the trick about ORAM is that you need to keep state on the client typically. So here we have many clients that are not interacting with each other. So there's an issue of what do you do about the client state? And so one thing you could think to do is to store the client state in the database. Exactly. But the problem there is now you have to worry about malicious clients. So if a malicious client corrupts the state of the database, that could cause some later user's request to leak information, say, about where that user is writing. So at least we looked at ORAM, and we were not able to figure out a way to do it more efficiently, where we'd have the property that both the clients don't need to coordinate, and we can tolerate malicious clients that might try to corrupt the state of the database or cause an honest client to do something incorrect by corrupting the state.
Thank you.
Thanks.
So even assuming honest clients, if I'm going to send a message, I need to wait until a few other people also send messages right before the anonymity is secured. The concern that I have is that there might be a bias, because if I'm sending you a message, it is quite likely that the responding person will, like the responding set from the anonymity set, or the responding subset from the anonymity set will include you. And therefore, if the anonymity set is not particularly active at this particular point in time, the anonymity set will comprise of the people I have instigated into an active state by sending them a message.
Right. So you're saying if the anonymity set changes over time, for example,
Right.
you can use the fact that it's changed to sort of intersect the anonymity sets and figure out or make some guesses about who's saying what?
It seems that I'm inherently causing a bias in the anonymity set by causing certain people to be more active by sending them a message and expecting a response. So say that this is sort of a private messaging scenario, right? And the anonymity right now, so say our server is based in San Francisco and it's midnight and everyone's asleep. Okay, so this anonymity set is not particularly active at this point in time. I send a message to you and 3 other people. By sending this message, I'm causing a bias in the anonymity set that, which means that you and the people I've sent the message to are more likely to be active right now and send a response.
Yeah, I get you. So I think the issue is sort of about the meta protocol that you design around this database that you can write privately into. And as you say, it's very important that you construct that meta protocol in such a way that you don't leak information by virtue of the way that works. So for example, a protocol that works by I check to see if there's a message for me, and if so, I respond, is not going to be a good protocol to use, because that obviously leaks information about over time about who I'm talking to and what I'm doing. So typically, the way these things work is if you really want security over time, you have to make sure that everyone is checking the system at some fixed time interval, or or do something out of band. But yeah, typically the way you protect against those attacks is making sure that the anonymity set is sort of as constant as it possibly can be over time.
Thank you.
I'll ask one more question. So you said you want to get better performance at scale than 1 million people, but I guess have you thought about the application of the anonymous messaging systems on college campuses that students really like, kind of like Yik Yak and Whisper, because those are usually less than 1 million. And they actually get like a lot of traffic with kids writing snarky stuff about each other, and you could disrupt the market and have actually good security where they all rely on a trusted server right now.
It sounds like a startup idea, Joe.
Well, that's what happens when you have 2 Stanford people chatting.
Yeah.
I guess with that, let's thank Henry.